Alright, we have a little ground to cover today because we are lacking 20 minutes a day for 2 weeks. 10 minutes a day for 2 weeks. So let's go over some of this together after you've kind of gotten at least a preview of the experiment. So I like to expose you guys to the scientific method in a different way because you've been doing scientific method for like 10 years of your life now. So let's looking at this experiment, let's kind of talk through the scientific method, and we're going to talk some more in our groups today. So looking at the experiment, alcohol vinegar, what is the reaction that you guys have this in front of you on your papers? Ben, is there a Ben? Yeah. Ben? What's the reaction in this first model? Well, what are the two things that are added together?
Oh, the alcohol and vinegar.
Okay, and what's happening? And what's happening in the mixed part? Can you see in the picture? Bubbles, so they're fizzing, they're bubbling. And then what else is happening? Madison, look at the data that's kind of before and after. What's happening?
The temperature went down 9 tenths of the, or 0.9.
So 0.9 degrees Celsius?
Yeah.
Okay, so there was some temperature changes and there's bubbling, there's fizzing. No more sophisticated than that, okay? So this is easy stuff right now. Now, thinking about that though, if the temperature went down, the thermometer itself is reading a decrease in temperature. Does that mean it's an endothermic reaction or an exothermic reaction? Take a stab at it, somebody. But it's being released, but what's detecting that release is the thermometer, right? So if the thermometer is detecting the release of heat, wouldn't the thermometer's temperature go up? So is it exothermic? No, it's endothermic. So we're going to start really kind of drilling into chemistry like in 2 units or 3 units on that. But the thermometer is a bystander. The reaction is the thing that we're really concerned about. So the reaction is actually taking energy from the outside, from the surroundings. It's taking it in. So the thermometer is reading that as, oh no, energy's going down. It's going into the reaction. It's endothermic. So that's something we'll talk about more. Number 2, did the room pressure change during the reaction? Jordan, looking at the model between before and after. No. So the room temperature or room pressure is what? kPa, right? Kilopascals is named after a nice scientist named Mr. Pascal. So everyone likes names that after themselves. So that's just an observation you're making. And that's called a constant, but this is a constant throughout the experiment. Number 2, what should these experiments observed during the mixed phase suggest chemical changes are happening, Nick?
The bubbling and the temperature change.
Right, so we're going to talk about physical changes and chemical changes later, where those are 2 definite chemical changes. And then we already talked about we said there was a decrease in temperature. So easy so far. Look at Model 2. I know none of us have really looked at Model 2, we're probably working on Model 1 still. So these are results from that same experiment. Look at it, and then look back at Model 1. Tell me, which of those trials there is representing Model 1? Model 1, good. So we saw that because what's in the picture on Model 1? Okay, so that temperature change is the same, and what? Number of Alka-Seltzer tablets, there's 1, and there's 1 in trial 1. So as they kind of continued this experiment, they ran multiple trials. What is the one thing that they were purposely changing? So this is 6A. What variable is purposely being changed, Kiara?
The number of Alka-Seltzer tablets.
Okay, and is that called, so you're purposely changing the number of Alka-Seltzer tablets. Is that called the independent variable or the dependent variable, Lucas? You said that with hesitation. Good guess there. So yes, it is independent because and you may have learned this in biology, this is the way I've always remembered it. If it's something I am changing, it is the IV, independent variable, IV. Okay? If I change it on purpose, it's the IV. The result of that is what I'm looking for. So the result of that was what in this particular experiment, Morgan? My changing of the tablets, of the number of tablets, I was doing that on purpose, right? It changed something else though that I was measuring. Right, the temperature. Is that called the IV or the DV? The dependent variable or independent variable? Dependent, because it depends on the independent, right? So the temperature change depends on the number of tablets placed in there. Good. What variables shown in Model 2 were remain constant in all experimental trials, Jillian? And the 3. So we got volume of vinegar, room pressure, and initial temperature, and it was approximately room temperature, but not quite. Okay, so those are some data tables and giving you more experimental setups. Let's talk about the scientific method, okay? So we are going to get into groups in just a second. You can leave this warm-up sheet at your desk. We'll kind of continue the warm-up sheet on another day, not today. We are actually going to go to lab stations. We have 2 activities. It'll take us no more than 15 minutes. And we're going to come back and just kind of see what we're doing every day here. We're going to do an activity for a little while. We're going to take some notes, and we'll do some practice. So that tonight you are successful on what's your homework tonight? What does PS mean? Problem set. Good job, guys. Okay, so problem set 3A. Aim close to choose. So bring some shoes tomorrow if you're a single wicked person. Where would you find problem set 3A? On my website. Where? Well, it's listed in our homework, but it's not there. Has anybody printed the student packet? Yay! Okay, so the student packet is under Unit 1. I showed you this yesterday. It's under Unit 1 documents, and it says Unit 1 student packet. That's where all your homework is for the unit, okay? Except for those couple of reading guides I did print for you. And you do not have to print it. You can pull it up on the device. That's totally fine, but it's there for your convenience. So when we get to our groups, you do not need a piece of paper, actually. Scratch that. You don't even need a pencil. I've got markers and color or crayons back there for you. The first thing we're going to do is we're going to meet our groupies. We're going to hang out them for about 5 minutes, and we're going to write down as many words that come to mind about the essentials of an experiment. Okay? Some of which we've just talked about. Some of them are going to kind of be more scientific method-y vocabulary. After that, we're going to work with a chemical that we have on our table, and it's just on a SDS sheet because I can't bring out chemicals till every time there are a lot of contracts. And I'll walk to that in a second. So, your groups. I'll let you guys choose your groups eventually, but I just don't know you yet, so I got to work on names still. So, here are your groups. Look for your name. You don't need anything but yourself and a smile. And my groups are 1, 2, 3, 4, 5 in the back right here in front of you. 6, 7, 8, 9, 10 right here. 30 seconds, go. And choose a writer for the first activity, but you need to repeat. Instructions are on the board. So choose one person to write from the color paper and we're going to take that away. Choose a writer.
Because I was going to say,
I heard it.
wait, what?
Looks like you're the writer. I don't mind sharing.
So basically, no words on the page. No words on the page. It does not be organized. Be a collage. Collage of vocabulary. Things that you think of. You guys want markers? There's markers on the table over there. So if you write on the essential parts of the investigation, so on the page.
Does that look right? That looks right.
Yeah. C6. Yeah.
Hypo.
Oh, yeah. She's like, this is honors chem. They can't even spell hypothesis.
That's okay. You'll learn how to spell copper 2 sulfate pentahydrate. So
No.
that's easier than hypothesis.
Data. Well, here.
She stole both of them.
I know. Where did steal one?
Beautiful. Okay. As you're coming back, please pull out some paper or notes. Pull out some paper for notes. Oh. I remember this right now, separate. I wrote down 2 things that are excellent. Okay. Some of you have before, if you've explored my website at any extent, you've probably seen the word Celly out there. It's basically a way you can text me really quick questions like, I cannot get number 3 on problem set 3. Please help me. If you don't want to come in the morning or come at lunch or come after school. So it's a quick homework question. It should not be like I'm writing essays back and forth with you. Celly is an app you can download or you can just text to, text 23559. If you'd like to do this now, that is fine. So that is the number you're texting. And to that number, you text at CMHS capital honors capital Chem. So you text that number, this message at CMHS honors Chem, it'll prompt you for a password. The password is I love chemistry. I do not focus on my website because I don't want any weirdos on so okay? So everybody wants to be on it. But it's an easy way for you to communicate with me. It's also really easy for me to remind you of quizzes or tests or things that are happening in school. Yeah. Yeah, it's all one word. Sorry. This is all one word. CMHS is caps, H is caps, and the C is caps. So that's one thing I wanted to make you guys aware of, especially if you want to ask me any questions. Please don't text me after like 10 p.m. I need my BBC. But the absentee thing I'll ask for shortly. You guys were your absentee buddies on your syllabus yesterday? Yeah? I'll ask for those names later. Because I just need that. And this information is on my website except for the password. Okay? And that's just for you if you're I text, so you can text me, that's cool. And I keep getting out of the messages have begun. Yes, cap CMHS. Multiples of you are getting in, okay. Alright, so while you're doing that, I will start telling you about notes. Now, notes, I do not ask for you to write down everything. I ask for you to write down what you need to, because you'll see some things that are repeated from the reading guide, and I will give you a reading guide back, so it's practically like a pre-notes page. The things that are highlighted, I feel are the most important words, and you can, of course, write down more explanations. Sometimes the things that I say are more important than what's on the board, so I do recommend you try to write down what you need and listen, okay? So, when we're talking about chemistry, we have these lovely people, the alchemists, to thank, because they were our first chemists, or true chemists. They worked, everyone thought, oh, it's magical. They're lighting these things on fire, they're causing these colors to change, they're doing all these, magic tricks, basically. So people did not really give them the role or the title of scientist back in the day. They were called alchemists, and we've probably heard of alchemist or alchemy before. So if you can't explain something, it's alchemy, right? So that's a word we've thrown around. But they are who we thank for the tools and the techniques that we use in chemistry today. So the tools and techniques that scientists use today came from the alchemists back in the day. One specific person I like to recognize, and with chemists, we do not do things necessarily, well, we do. Sometimes we do experiments for pure knowledge, for pure science, just to discover something, right? But most of the time our experiments are targeted towards problem solving. So one of the biggest problems right now is the energy crisis of the world. We don't have enough fossil fuels to get done what we need done. So we're reaching out and trying to do all these other, trying to search for alternate energy sources. So, of course, that is a problem that the world needs solved. Most of our methods have logical methods to them, okay? It's not like, I'm just going to throw this and this together. You do have some logic behind what you're doing. It's not based off a belief system. It's logic. This guy, Antoine Lavoisier, is somebody you probably read about a little bit in your book you were reading. He is responsible for one of the biggest laws that we all kind of just take for granted at this point, is the law of conservation of mass, or the law of conservation of matter. So I like to abbreviate as often as I can to save your little fingers. Law of conservation of matter. And that's, we've explored a little bit of that probably in middle school. We'll explore it more now to this unit. And it just means that as you go from reactants to products, Mass is conserved. Mass is neither created nor destroyed. You've heard probably that before. Who's heard about that one before? Perfect. I knew you guys would. Okay. His main way of confirming the law of conservation of mass was through combustion. And he analyzed combustion. What does combustion mean? Tell me one word. Boom! Explode, right? Okay. So what is it reacting with to do that though? Most combustion is going to react with what? To make thank you, oxygen. I didn't ask that very well. It's going to react with a specific gas to make fire, right? It's going to react with oxygen. Okay. Most combustion reactions actually involve something called a hydrocarbon. Who's heard of a hydrocarbon? From biology? No? What do you think two elements are involved in hydrocarbon? Hydrogen and carbon. Generally, we don't write H and then C, though. We write C and then H. So you've seen something that probably has a C and an H in it. We've also seen something that has, they're called oxygen-containing hydrocarbons, so they're CHO. Okay? What compound has CH and O in it that you know of? Fantastic. I don't know the formula off the top of my head, though. I'm going with something that's in chocolate to make it sweet. Sugar. What kind of sugar? Glucose. Formula. C6, 12, O6. Oops, O6. O was already there. O6. Good. So that's glucose plus oxygen. What does it make? Alcohol. It's cellular respiration. What is it making? Yes, but what's in the fire extinguisher? Carbon dioxide and
water.
Thank you. Whew, that was like pulling teeth. That's biology. Okay, so that's cellular respiration right there. Good. Combustion in your body is happening, and there's many explosions, and it's making some ATP. Depends on how efficient you are. But we've been exposed to combustion before. Good. Okay, moving on. Most of the time my rule is majority rule, so I move on when it looks like everybody's done, or when I'm done. So, does this look familiar? If you did your reading guide. Yes, okay. Please do not write down all of these quantities. You already did that. Let's look at some of these though. So, it's important for us to kind of come to the consensus that we will use the same units because it is easier to understand other people's work and labs and data and results when we're working on the same system. Well, that system is the SI system. And all chemists, all scientists use it for consistency, except for America. Okay? We use what? We use the American. We use a different system. So if you're driving down the road and you're looking and you're like, oh, the speed limit is what? Miles per hour. If you go to Canada, kilometers per hour. So they're on the metric system, right? So meters is where we're getting kilometers from, right? Another very common one that most people do use it are grams or kilograms. We don't use grams and kilograms. We use pounds and ounces, right? And then Kelvin. Kelvin is something that we see a lot in labs, but we don't always use it. Celsius is probably our more common one, but except for us, we use Fahrenheit. But we're not going to use it here. We're going to use Celsius in our class, okay? We're going to try to mesh with these lovely scientists. And then milliliters and volume, we don't use that. We use cups and gallons, right? Pints. So we are going to go with the scientific way of reporting data, okay? So we'll use these units a lot. And I've circled the most important ones because those are going to be this unit. The other ones come in later units. So what measurement do I get if I combine grams and milliliters? No. If I combine grams and milliliters, grams per milliliter, does that ring a bell? Density? That's density? Sorry, you're not just picking up what I'm saying here. So that's called a derived unit because you calculate it. You calculate density by taking mass divided by volume. So if I ask for a derived unit or an example of a derived unit, and you think I'm speaking a foreign language, derived just means calculated. So density is an example of that. Area is also an example of that. So you think derived units or something weird, they're just a calculated unit. right. So moving on. We're hunky-dory here. So speaking of Kelvin, how do you get to Kelvin? Thought I saw this last night, but Celsius is your way to start with. So if I tell you room temperature is 25 degrees C, what is it in Kelvin? If I tell you that is the formula that we work with. 290. 298. Good. Kelvin. Okay. And room temperature is one that you need to kind of memorize because we will use room temperature a lot. So if I say something's happening at room temperature, you're like, oh my gosh, what's that temperature again? It's 25 degrees C. I'll remind you of that for a while. Let's get down here. This is easier math. We all should know water boils at 100 degrees Celsius. What is that in Fahrenheit? 212. Somehow we know 212 over 100 sometimes. But this is the one you should know. What is that in Kelvin? 373 Kelvin, because you're just taking 100 plus 273 to get 373. And what is the freezing point of water in Kelvin?
273.
Right, 273, because you're taking 0 plus. And you'll notice I don't write the degree mark in Kelvin. It's just not, you just don't write it. You write it in Celsius and Fahrenheit though. And body temperature, I'll remind you of that one. I say to know, you definitely need to know room temperature. The body temperature one, I can remind you of. That's fun fact, 37 degrees C. Sounds like it's cold, right? It's not. Right, can I go on? Thumbs up, you got this? A couple of people are so right. Okay, let me let them finish. Now we're going to get to your question on sig figs. Okey-dokey, and I am videoing right now, so you guys can always go back and go to a specific slide if you want to hear anything. Okay, thumbs up if you know the metric system. You know the basic metric system. Yay, okay. Kilo, hecto, blah, blah, blah. You may not remember it that way. You might remember it this silly way. King Henry died by drinking chocolate milk. Yes, yes? Some of us? Okay. So the way I normally write it, though, is King Henry died in caps. And I don't know why I didn't do this way. And then King Henry died by drinking chocolate, that's lowercase, milk. These are all capital letters because all of these prefixes represent a number that is larger than 10. These prefixes are representing something that's smaller than a base unit of 10. So it's just a scale that we're working with. And you have been exposed to this probably quite a few times in your life. But anything that's a kilo is 1,000 times greater than the base unit. And base units, right here, oopsies, base units here that we will commonly deal with are grams, meters, and liters. So know those three at least, and those are our base. So you can convert grams to kilograms or to milligrams. You can convert liters, anywhere in between. Hectoliters or centiliters. We can add that prefix to anything. And I'll show you how we're going to work with them a little bit today, but we're going to start something called dimensional analysis, which is like chemistry math, tomorrow, or Thursday. So chemistry math is a little tiny bit different than regular math, and it's just a way that we kind of process the problem. So if in your normal life, when you're converting 53 grams to kilograms, how would you normally do that? Decimal swoops? Yeah? Yeah? Okay, so I just, to remind you how you would normally do that. Normally you would go, okay, grams is which part of King Henry died by drinking chocolate milk? Grams. It's base, right? So you are here. So if you're here and you want to get to kilograms, well, that's over there. So you have to bounce back. Died Henry King, right? You have to bounce back 3 decimals. So you take your 53 grams. Where's the decimal at currently? Behind the 3. Okay, and you go 1, 2, 3, replace the decimal there, 0 kilograms. So what that means is 53 grams is equal to 0.53 kilograms. Sorry, that's really close. So that makes sense though. How many grams are in a kilogram? 1,000, right? So 1 kilogram is huge, which is 1,000 grams. So 53 grams ain't even touching that. So that's not even a full kilogram, so it makes sense. So kind of review your work and make sure it's logical, because we try to stick with logic here. So if you're taking 9.84 liters to deciliters, where's deci on our number line here? 1 to the right, correct? So you're taking your base unit of liters, which is there. You maybe use a different color. And you're moving your decimal once to the right. So you're moving this decimal, which is here, once to the right. So that is 98.4 deciliters. Good. Okay. So many, many deciliters go into a full liter. So you should have a lot more deciliters than a liter. So you need to know which is bigger in the units. We'll work with this some more. I'll give you something to process. See, some more writing still. Okay. So this is a quick blurb review of pretty much everything right now. Thumbs up if you know how to do scientific notation. Scientific notation saves you so much writing. Because if you have to write this number out as often as you're going to this year, you're going to cry. Okay, I don't want anybody crying. But if I wanted to record this to scientific and appropriate scientific notation, the coefficient in the front has to be between what two numbers? 1 and 10. So you must be between 1 and 10. So what number do I need to record to represent this? 6.02. And then times 10 to the sum number that gets me from this decimal where I placed it all the way over here. And I know you're counting, it's 23. Good job, guys. Okay, so 23. So if you have to write that, it's a waste of time. So scientific notation will save you time. If you're going to a bigger number, it must be a positive exponent. If it's a smaller number that's less than 0, then you need to make it a negative exponent. So it's really good for very large and very small numbers. Good. Thank you. I need feedback, because if not, I roll and I don't know if you guys are good or not. Okay, so let's just do number 1 up here. Tell me that you can do this. What is that in scientific notation? Raise your hand. Go for it.
3.880908 times 10 to the negative 3.
There you go. Because you're putting the decimal there, and that's 3 removed from the original. There you go. And so is that a measurement? No. Why is it not? It doesn't have a unit. If I wanted to make it a measurement, I would have to have a unit with it. Measurements always have units. So that's why those units that we were talking about earlier are important to know. Okay, I'm not going to go on. All right, so let's take a break real fast. Who likes basketball? What? Well, b-ball on the side on my free time. So, who wants to waste some paper? Yeah. Let's. It's for an educational purpose. I need like 10 volunteers to give me a piece of paper, and all you do is tear it out of your notebook. If I have to pass out paper, I can do this. Oh, here, look, I already have 3 made basketballs. 3 made basketballs. There you go. Look, 3 made basketballs. Are you with me? Look, I volunteered right there. Thank you. So, I'm going to need maybe like 2 more. Let's see here. Please, can you guys catch? Never catches it. Okay, so, if I were playing basketball, I, of course, am going to aim for the what? The basket, the hoop. I'm not good. I don't even hit the rim. It just swooshes. Okay, swoosh. So the accurate goal here is to swoosh. Now let's go ahead and see. Let's go back rows first. Just farther away. Go for it. Okay, everyone. Shoot the basketball. Air ball. Did I? Okay. We had 1 accurate shot. Who was that? What? Okay, you can be on my team. These other people, did anybody hit the rim? Okay, so we were really almost accurate to hit the rim, right? Accurate was in. Now, if anybody was clumped here, so right, you guys can't really see, but there are 4 right here, okay? These are very, very reproducible. So I had 4 people reproduce this almost exact shot. Was it accurate? But they're clumped together, right? That's reproducible. So that means they are very precise. They kept missing the basket, man. They were so precise, they kept missing the basket. But that's okay. If your measurements are reproducible, that is totally fine. Can you be accurate and precise? Yeah. If you're like swoosh, swoosh, swoosh the whole time, you're accurate and precise because you're reproducing your good shot. If you're missing the basket on the upper right side of the backboard every time and it's just hitting the backboard 100 times, you're still very precise, but you're not accurate. So, can you be? No, I'm going to exhaust it here. Anyway, so these two definitions are very important to know the difference between them, but also know that you can be accurate and precise, or you can just be precise and not accurate. You can be sometimes one without the other. So the closeness and series of measurements just means that you have reproducible measurements, and you keep reproducing the same thing over and over and over, even if it's wrong. Okay, but accuracy is usually where our goal is. Now, we're not perfect. Like we can see those basketballs around here. Okay? We're not perfect. We sometimes have error. I mean, like, let's be real. We always have error. We are humans. Is it better to have like 1 to 5% error, or like 90 to 95% error? 5% error, right? You want to have low error, okay? So low error, and I'm going to get down here in just a second. Low percent error is better than high percent error. Did I go too far? You guys okay? If I need to scroll back, let me know. So when we're talking about error, we're always basing our experimental result from the actual value we wanted. So this person didn't have that much error because they were close to the basket, but like these people back here had a lot of error because they were farther away from the basket. So the difference, and when I say difference in math, what does that mean to you? Subtraction is the part that actually matters. So if I'm doing absolute value though, does it matter if I do experimental minus accepted or accepted minus experimental? No. It's a positive value when you do absolute value, so it doesn't matter. So I always say percent error is actual minus experimental over actual times 100. So A minus E over A. And if you just write that down like 3 times, you really should get it, okay? But experimental error is something we're going to probably report in like every other lab. So just be familiar with that calculation. Yeah. This is my version. This is how I write this. So I do actual minus experimental over actual. And it's because actual and accepted are basically the same thing. And then it doesn't matter if you subtract this from whichever one because you're doing absolute value. So it's almost like you can't get it wrong unless you put the wrong value on the bottom. That's when you get it wrong. So let's look at this. And this requires you to remember what room temperature is. So you measure room temperature to be 28 degrees Celsius with thermometer. What is the percent error? Is that the percent error, or is that the error? So tell me how I calculate percent error. Okay, so what is my what is my accepted value of temperature for room temperature? Accepted, the true value. 25 minus your experimental value, which is 28, over what? Accepted, which is 25. So times 100. So that's 3 over 25, which is like 12.5%, I believe. 12.5. So if that is 12.5% error, then is that good or bad? I mean, it's not bad, it's not horrible. Like we really want to be like below 10 if possible. Okay, so far not too bad. Review, percent error. Okay, now let's go to oh, sorry, I forgot this. People sometimes still can't really realize the difference between accuracy and precision. So if you want to read that, the green part is the really important part. If you want to take a picture of it, go for it. I feel like that's like the best explanation, really long-winded explanation of this concept. So you're talking about reproducibility and consistency in measurement, and then versus nearness to actual value. And you can also see this up anytime you want to online. So this person here, this student, 3.54 grams, 3.55 grams, 3.56 grams. That's very reproducible. They're very close in their measurements. That means they're very precise. But what if I told you the true value is 3.5? What would you say? Very accurate and very precise. What if I told you the true value is 6? Not accurate, but precise. So So you just want to be able to verbalize that. Okay, now, when we're talking about measurements, let me go forward here. Don't look at this yet. Look at the pictures. Max, tell me, how long is this little rectangular thing?
1.25.
1.25?
Attention teachers, if you have not done your attendance yet for any block today, please go ahead and do your attendance. If you've not done your attendance for any period today, please go ahead and do your attendance. Thank you.
Okay, so, yeah, people are having a hard time with attendance. Anyway, so 1.25, so you are accurate. You think that you are for sure it is a quarter of the way down, and you're sure of these last two digits. We shall see. Connor, give me another estimate here of this.
1.3.
1.3. See, I know for sure, and we all know for sure it's over 1, right? But this is a really crappy ruler because it doesn't have what on it. Where are those tick marks from? It does not start with P. It starts with a G. Graduation. Thank you. Okay, so these have graduations, and this one does not. Okay, so GP, of course. So this one right here is not so good. So I would never want to use this ruler because it's only accurate for sure at every single digit, every one. This is more accurate because you have dash lines, the graduations, and it's accurate to the 10th digit, to the 10th placeholder. This is only to 1. So now let's make a new estimate. Michael, right here, with this lovely ruler.
1.3.
1.3 is exactly.
Or a little less.
A little less, so like what?
1.29.
2.9. I like it. Okay. Now, if you're looking at this one, and somebody else might estimate 1.28 or 1.27, and that point is just to show you that everyone can measure something differently. So there may not actually, there is a true measurement, but everyone estimates, right? This digit here, what's his estimated one? This is absolutely true. And the 2 part is absolutely true because it is a hair less than the 1.3 mark there. So these 2 are true values, and that's your estimated one. So everybody can have a different estimated digit. And over here, this 1 is the true value, which is the estimated value. The 3. So what we're talking about here is not telling lies about our measurements. We all want to say, this thing is 1.300000 centimeters. I'm like, your ruler is awesome, right? Because you have so many graduations that I know for sure down to like the 5th or 6th decimal. So we don't want to lie. I know it sounds silly. We don't want to lie about our measurements by recording too many digits. And that's where we get into significant figures or significant digits. Only the ones that are for sure are the ones that you record, plus the one that you get to estimate. So this should look similar to what you saw last night in your book, but it might make more sense now, like what's the importance of it. So significant digits, in our values, we always have to count up and assume that all of them are known. The last one is the estimated one. So if you don't write down anything else, the green part is kind of important, or the red part there. 1 digit is estimated. Now, what's really determining the accuracy of your numbers or the number of sig figs you can record? It's not your brain, right? You know numbers, you can spell them out. It's what you're measuring with. You have really good equipment, like this really awesome ruler over here on the right, or you've got really not so great equipment, like this one on the left. So your measurement, your apparatus, your equipment is what that means, is the part that's limiting your accuracy. Yeah.
So significant figures aren't like a group of numbers, like one number, and then the significant figures are like
Well, the significant figures can be in decimal point or before. So the significant figures are different for every measurement. So if I were looking at, and I'll actually show you on the next page, if I were looking at this number, this measurement, the 1.25, that has 3 sig figs in it. Okay? The one below it, this 1.3 number, only has 2 sig figs in it. Which is more accurate? The number with more significant figures, because they're known digits. That means like you know for sure they're right, means you're more accurate. And I'm going to get into more of that now.
And then does that mean that the one that was estimated is like the 3 on that one at the bottom?
Mm-hmm. Question?
On the first ruler, the 1.25, would you round for that? Would you just go 1.3?
It depends on the number of graduations, I actually, this is, it's impossible to record that. I'm just using it as an example. You have to record to 3 because it's estimated. Good job. Yeah.
For the first one, for the first one, is the 3 actually a significant figure?
It is considered a significant figure because we include the estimated digit as a significant figure. It's part of the rules. You record, or you call them all significant because we all know, if we understand sig figs, that everything up to that last one is true. The last one is estimated, but we still have to accept whoever's estimation it is. Okay, so let's look at some rules. And this is on your lecture notes that I printed for you in the packet, or in the folder I gave you. Pull those out from the back of your reading guide paper. So now we're going to start to learn more about how you count the significant figures in a measurement. And so, like I said, the measurement device does really limit the accuracy. But this specific Atlantic method is the best way to know when to count a 0 as a significant figure and when not to. So if I give you an example of 1.20 centimeters, you'll notice that the decimal is present, right? Think of your map of the United States. Where's the Pacific Ocean? California. Okay, where's the Atlantic? North Carolina. Okay, so over here is where we're going to start counting at the Pacific Ocean. So if the decimal is present, you approach this measurement from the Pacific side. So you start counting here at the first non-zero digit. Is this a non-zero digit? Yes. You start counting. Once you start counting, don't stop till you get to the end. So you count 1, 2, 3. There are 3 sig figs in that number. Okay? That's because the decimal is present, and that means I'm accurate to the 10th digit, and I estimated the 0. So there are 3 sig figs. But what if I wrote this number? The decimal is, so it's absent, correct? So it's absent. You start counting sig figs from the Atlantic side, which is the right side, at the first non-zero digit. Do you count here? No, you start counting at the 2, and you keep counting that way. So 1, 2. How many sig figs? 2. So you're only accurate, you only know for sure to the 10th digit on the integer side, right? So this 0 here is estimated. Yeah.
So what if it was like 1020? Would there be 3?
1020, because you start counting at the absent, the decimal is absent, so you start counting from the Atlantic and you go boom, 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 3. So what about this number? How many sig figs? 1. What about this number? 6. And that's because I'm saying I know for sure, people, that it's at least this much, and I'm estimating that. It could have been 100,001. And maybe it's 100,000 straight on. So the accuracy is limited by the device you're using to measure, but we don't always have devices to measure it. Sometimes we just read from paper. So this is the method you will use to count sig figs. Let's do a couple of these. Shout them out as you go, and this is on your paper. You can write it as an example on your paper. Okay, so look at A. Takes like less than 5 seconds. Decimal is present. Start from the Pacific, and you say 1, 2, 3. 3 sig figs. Good. Decimal is present. Start from the Pacific. Count. 4, right? 4 sig figs. Good. Decimal is, so absent, right? Absent, start from the Atlantic and count. 5 sig figs. Keep going. Decimal is present, start from the Pacific, and how many? 6. E. Decimal is, so absent, start from the absent Atlantic, right? AAPP, okay. Start from the Atlantic and count. So ignore the zeros and use a 2 sig figs. So far, D is the most precise of them all because you have a lot more sig figs. So that's how we're going to be counting. But we now have to build on this. We're going to start rounding. We're going to start adding and subtracting, multiplying, dividing. And they're just rules for everything, okay? But you'll kind of get the hang of it if you practice. So let's keep going through a couple of these. The rounding part, I think, is the hardest to understand at first, but then you kind of get it, okay? When you round a number, like 1.5, what do you round it to? 2. You round a 102, what do you round it to? 100. You're not changing the number really, right? You're just like tweaking it a little bit. So 102 is really still close to 100. 1.5 is still really close to 2. So if I want you to round this number and only allow for the number to have one significant figure, the number is still going to be in the realm of 50,000, right? You're not allowed to change the magnitude of it. You're only allowed to tweak the numbers after it and the decimal, okay? So if I want to round that to 1 sig fig, the way I start is by looking at the number, starting on the left side, because this time I'm really concerned about the magnitude more so than Pacific Atlantic kind of thing. So if I'm looking at it, I must record the 5, okay? And after that, everything past here must be recorded as a 0 to allow me to have 1 sig fig, but still keep my scale of 50,000. So you'll notice that I looked at the 5, and I didn't actually say this part. I looked at the 5, and I looked at the next number. Does that 0 influence the 5? No, it doesn't round it up, so it's staying as 50,000. And that has 1 sig fig in it, correct? Okay. So the rounding part just it's got more steps to it. And that's exactly what I just said right there. Okay, so start counting sig figs from the left. Take the number of digits that you require. So I've got like 1 through 8 down here. And then the rest must be zeros. Now, sometimes we might have to change the way we write the number to meet the sig fig requirement. So let's look at another one. This little thing you do keeps coming up. Sorry, guys. So looking at the 2, we want 2 sig figs. So I'm going to write 5, 0, because that's the first 2 digits. Does that 6 influence the 0? Yes. So does this stay a 0? No, it goes up to 1. And then the rest are zeros. Okay? So we're still in the realm of 50,000. It's 51,000, so we round it up. Next one. I see 506, 506. And then does that 6 get influenced by the 0? Nope. So it stays, and then everything else is a 0. How many sig figs here? 3. I'll do one more. So now I have to record 4 sig figs. So I look and I go, okay, 5060. Does that 0 get influenced by that 0? No. So 5060, and then I record the last 0. Guess what? Did I write that? Oh, sorry, I put 560,000. Sorry. There we go. This number is the same as this number. I can actually write this correctly here. There we go. These two numbers are the same. They can't be written the same though, because I'm asking for 2 different variations, one with 3 sig figs, one with 4 sig figs. So how can I rewrite 50600 as 4 sig figs? What's a tool you have to write big numbers in a different way? Scientific notation. So I can write this as 5.060 times 10 to the to the 4, thank you, in milliliters, whatever this is. Okay, so this way of writing it means that the sig figs are held before the times 10 to the 4th. So how many sig figs are here? 4. So scientific notation is a tool to use when you need to record a specific number of sig figs. And you'll kind of understand the more important stuff behind this later, but we're still working on mastering what sig figs are probably. Okay, so we got about 10 minutes left. This class flies, I swear. This part is on your notes as well. Do you see them? Okay. What do you notice is the main difference between adding, subtracting, and multiplying, dividing? Look at the rules. It's the thing that's blatantly different. One is really looking at what?
One is looking at figures and the other is looking at decimal places.
Right. So we need to kind of keep those 2 rules separate in our brains, okay? So when you're adding and subtracting, you're going to count decimal places. And you are concerned with, I'm going to start with adding and subtracting right here. So let me make up an example. 2.2 plus 2.22. Okay. Add these up for me. 4.42. Okay. Centimeters or something. There we go. So we have these 2 measurements. Which of these is our weakest link? Which one has lesser decimal places? Right. So this one has 1 decimal, and this one has 2 decimals. So the weaker link really slows you down, right? So if you're cross country, I'd be your weaker link. I'd be the one that's like passing the baton. Go, go. Oh, that's track. It's not cross country. So if you take your 1 decimal and you use that to influence your final answer, that means this final answer must only have 1 decimal in the end. So your job is to go, okay, 4.4. Does this 2 influence that 4? No. So the answer is 4.4 centimeters. Boom, done. So you're using your rounding skills and your sig figs, and your rules of adding and subtracting in the same problem, okay? So same thing, 2.2 times 2.0. Let's go 2.00 here. Let's do 2.2 times 2.00. What is that? .4, right? Okay. Now you're not sure. You're like, do I record 4.4? Is it 4.40? That's where we have to count sig figs. So the weaker link of this one is which of these has lesser sig figs?
The 2.2.
2.2. How many sig figs are there? 2 sig figs. Because you said present, Pacific, 1, 2. This one is present, Pacific, 1, 2, 3. So there's 3 sig figs here. So the weaker link is the 2 sig fig one, and that just means it's limiting your accuracy or your precision of your final answer. So 4.4 will be our final answer because it's recorded to 2 sig figs right there. So you just have to use these rules a lot to kind of get the hang of them, okay? And my joke is, you know all the words of all about that base, but not your sig fig rules. So we'll work on these. Okay, so let's go work on, let's just do these first 4 and that's it, okay? So 11.075, have a calculator phone out to calculate real quickly with me. The more active you are with me, the more you remember when you leave here. Okay? So let's first get our stuff out. Don't calculate just yet, okay? How many sig figs are we multiplying, dividing, adding, or subtracting? Dividing, so which rules are we using, sig figs or decimals? Sig figs. How many sig figs are in the first one right here? 5 sig figs. See, now you just look at a number and you're seeing them. You're seeing the number of sig figs. How many sig figs are here? 3. Weaker link? 3. So in the end, you only need 3 sig figs. Now calculate. Okay, 11 point. Tell me the full number.
0.8720.
Stop right there. That's good. Okay. So long number, right? Big fat lie is what I call that. I don't know that to that accuracy. I only know it to 3 sig figs of accuracy. So I need to look at the rounding rules, which are look at the first 3 digits. Does that 0 influence that 2? No. Answer is what? 0.872 units. Grams per milliliter, which is the unit of density. Okay, so I like to see your first number sometimes, and then I like to see your true answer after you round those sig figs. Okay, how many sig figs in here? I'm sorry, multiply, or add and subtract. Multiply, so you count sig figs. So I'm telling you your thought process. You count sig figs. How many sig figs in this one? 2, because the decimal is absent. Atlantic, skip. There you go. 1, 2. So there's 2 sig figs here. 2. Win-win situation. You can't get it wrong, right? So 140 times 35. 4,900. Ooh, that's kind of nice. What's up with this right here?
Since it starts with the Atlantic, it doesn't start until 9.
So you don't. So you already see it's already recorded 2 sig figs. Is it correct then? Not all the way. What's wrong? What is it? Centimeters squared, because it's centimeters times centimeters. Good. That one was good. Easy. Next one. What's your method of determining the weakest link? Yes, decimals, because we're adding and subtracting now. So we have 1 decimal, 2 decimal, 1 decimal. What's our final answer recorded as? 1 decimal. Add 5.28, 15.5. Okay, what do you get? Full answer?
42.78.
7.8. With units here? Centimeters, because when you add, you just take the unit as is. this must be what? Rounded, because we only can record one decimal. So does the 8 influence the 7? Yep, so 42.8 centimeters. Okay, D is the only tricky one, okay? Tell me what I do. Okay, so you add. What? Lies. How many decimals are recorded in the end? 0. This one is my weakest link because there's 0 decimals there. 2 decimals here and 1 decimal here. So when you get your final answer, you get 0.5, right? Right.
There's no decimal in there, right? So you round it up to 20.
Yes. So it's good to at least maybe write out the first full answer so that you look at it and you go, okay, 0 decimals, but this 5 does influence the 4, makes it go up to 2, 4, 6, 5 deciliters. Okay? Okay. So the last 2 minutes are yours. Sorry, I did not try not to do it all the time, but it's 10 minutes. Your guys' homework is a lot of this on problem set 3A. Okay? Come tomorrow with questions for me, please, so that can help you where you need it. I'm also here for tutoring if you guys want to chill and stay. Leave these, actually, no, pass up these to the front table for me. So just grab this from you now. The warm-up sheets we were working on.